So finally, we're going to summarize and review graphical models. So first, let's look at how do you calculate the rate of change. Recall that the rate of change, or the average rate of change, is equal to the change in y over the change in x, or y2 minus y1 over x2 minus x1. So for example, let us find the average rate of change for the points given in the diagram above. So first we're going to take the delta y, so the subtraction of the two y values, so 5 minus 20. And then we're going to subtract the two x values, 3 minus 1. So on your calculator, you can take 5 minus 20 in brackets and divide it by 3 minus 1 in brackets. And that'll give us negative 7.5. And the units for this average rate of change will be the y, so the degrees Celsius, over or divided by the time, which is in hours. So this is negative 7.5 degrees Celsius per hour. This means that the temperature is decreasing 7.5 degrees each hour. So how do we view our average rates of change? Well, first of all, if we have a horizontal line, the average rate of change is 0. The slope of a horizontal line is 0. Second, if we have any other line that's not horizontal, then we're going to have an average rate of change that is constant, or the slope is the same no matter what 2 points you take on this line. And finally, if it's not a straight line, then the average rate of change will vary. So notice if I take the following 2 points, we have this rate of change here, and the next 2 points, I have a much larger rate of change. The delta y is much bigger, given a similar delta x. The next thing we looked at is, how do you know whether you have a graph, a rate of change, or an equation that's linear, quadratic, or exponential? So first of all, let's start with a graph. So a linear graph will be one that, of course, is a straight line. A quadratic graph will be a parabola. So we can have a parabola that opens up or a parabola that opens downwards. And an exponential graph will be a graph that's always increasing or always decreasing. So a graph that looks like this, that's always increasing from left to right, or a graph that's always decreasing from left to right. The graph that's always increasing is called exponential growth, and versus our other one, which is exponential decay. How do we know the rates of change for these graphs? So for the rate of change of a linear graph, the average rate of change is constant. For a quadratic, the average rate of change is either increasing or decreasing by a constant value. And finally, for exponential, the AROC, or average rate of change, is increasing or decreasing by a constant factor. So what's the difference between quadratic and exponential? When we say increasing or decreasing by a constant number, so that means you're adding the same number to the average rate of change, whereas for exponential, you're multiplying by the same number to get your average rate of change. So recall, a linear equation is y equals mx plus b, or what we could use ax plus b, where the a is going to be your average rate of change, and your b is your initial value. For a quadratic, we have y equals ax squared plus bx plus c, and where c is your initial value. And finally, for exponential, we get y equals ab to the exponent x, where a is your initial value, and b is what we call our growth or decay factor. And our last topic that we covered was linear, quadratic, or exponential regression. So this semester, we plotted the data using Desmos. We're always going to say that linear regression is the model unless the scatter plot shows a curved relationship. And if the scatter plot shows a curved relationship, then we're going to use Desmos to see if a quadratic or exponential model best fits the data. We do that by looking at the coefficient of determination, or the r-squared value. So for example, this graph does not appear to be curved, so we're going to assume that this is a linear relationship between the variables. So we use Desmos to determine the line of best fit. So here's the formula that we type into Desmos for a linear relationship. And there is the a and b value we get for this model. So this tells us that y equals 28.6497x, so that's your rate of change, minus your initial value of 190.423. So using this model, then can we use Desmos to make some predictions? So for example, I can let x equal some number, and I can either put it into this equation here, or we can use Desmos to make a prediction by finding the intersection of x equals whatever number and the line of best fit. So for our next example, we see that the graph is clearly curved. So we say a non-linear relationship between the variables. We use Desmos to determine the curve of best fit. And notice here is the quadratic regression curve. Here is the exponential regression curve. Then we look at the r-squared values to see which one is closest to 1. And clearly, the exponential wins this. So that means our equation is y equals, we put in our a value, so this is our initial value, 481.161, times 1.20138, our growth factor, to the exponent x. So then using this model, we can either sub in an x value. So for example, we can say let x equal some number. We can put that into Desmos and find the point of intersection of that x value and the line of best fit. Here are the review questions that you can try.